Welcome. This is a time series analysis course. My name is Nicoleta Serban. I'm Associate Professor in the Stewart School of Industry and System Engineering. This lecture is on other time series methods, and in this lesson, I'll introduce an application of modeling heteroscedasticity for data that is observed of the very granular temporal granularity, specifically high-frequency data. Given a time series, the conditional variance of the time series at time t is the variance of the time series given the past values of the time series. In contrast, the unconditional variance of the time series at time t is simply its variance disregarding the variance of the past data. We commonly refer to conditional variance as volatility. In the simple case, when the time series data are independent, that is what happens at current time t does not depend on what happened in the past, then the conditional variance is the same as the unconditional variance, since the variability at time t is independent of the past data. Independence implies lack of dependence or lack of correlation. In the case when the time series data are uncorrelated but not independent, then we have that the covariance between any two variables in a time series is 0, meaning that there is not a linear dependence between any two variables in the time series. However, it is possible to find a transformation f of the variables in the time series such that f of x1, f of x2 to f of xn are correlated. One common transformation is the power transformation, for example, square power transformation. For this case, we do not necessarily have that the conditional variance is equal to the unconditional variance. What is high-frequency data? When data are observed at a very granular scale, for example, within a minute or even second time difference, then we say that the time series is observed with high frequency. Such data are observed in financial and medical fields. In this lesson, I will focus mainly on financial high-frequency data, although some of the modeling consideration will apply more generally. For financial data, the primary objective is to model the volatility at a lower data frequency, say the volatility within a day, from finer scale data, for example, minute level data. Another objective is to study market microstructure-related issues, for example, competition among related markets, strategic behavior of market participants, or real-time market dynamics. One main challenge in modeling high-frequency data in general is that we observe the time series of a very large number of time points. For example, the average daily number of quotes in the USD Euro exchange market could easily exceed 20,000 observations. And the average daily number of observations of an actively traded stock can be even higher. EKG monitoring, when diagnosing sleep apnea, for example, results in recording an EKG signal at milliseconds, and hence, over only 1 hour of sleep, we would record 3 million observations. Another challenge is that high-frequency data are often recorded with errors due to the involved process of acquiring the data. For various reasons, high-frequency data may contain erroneous observations, data gaps, and even disordered sequences of data. Third, high-frequency data typically exhibits multiple levels of periodic patterns, which can be challenging to be identified. For financial high-frequency data, additional challenges are encountered. Transaction-by-transaction data on trades and quotes are, by nature, irregularly spaced time series with random daily numbers of observations. Moreover, trades and quotes on multiple assets rarely occur at the same time, and trading activity varies considerably across assets. High-frequency data typically exhibit periodic intraday and intra-week patterns in market activity. It's well known that trading activities at any stock exchange are denser in the beginning and closing of the trading day than in the lunch hours. Furthermore, discrete price movements, non-synchronous trading, and bid-ask bounce resulting into the so-called microstructure noise may distort inferences based on standard statistical models. Because of these challenges, typical statistics and econometrics analysis and modeling do not contain the tools necessarily to properly handle and analyze high-frequency data. As I mentioned earlier, one of the primary objectives in studying financial high-frequency data is the variance estimation at less fine scale than the observations, thus using finer scale data. For example, estimating the variance within a day from minute-level data or the volatility within a month given daily data. A straightforward approach is to simply consider the sum of all observations within a month to obtain an estimate of the return for each month t. The example on this slide shows how to do just that, using the log return of a stock price from daily data for each month t. The main problem with this approach is that the variance of the monthly return computed as provided on the slide is the sum of the variance of individual returns plus the sum of the covariances of all pairs of the return time series. This second component makes this approachable unusable. Let's consider two examples. If the log returns are white noise, then the variance of the monthly return is the sum of the individual daily returns, or n times sigma squared. We can estimate sigma squared using the sample variance of the daily returns and plug in the formula of the variance of the monthly return. This is the ideal case. Things get more complicated if the log returns are not white noise, which is most of the time. If the returns follow a moving average process of order 1, for example, then the second term is now n minus 1 times the covariance of any pair of log returns within the t month, or the autocovariance at lag 1 if stationary. This can be estimated as provided on the slide. Thus, an important limitation of the variance estimator is that it depends on the model of the daily log returns, which usually is unknown. Second, we do not have a large number of trading days within a month. Thus, we have a small sample size, which can impact the accuracy of the estimator. An application of the estimator provided in the previous slide assumes that the sample mean of the daily returns within a month is 0. In this case, the estimated variance of the monthly return becomes the sum of the squared daily returns within the month t. Therefore, we can use the cumulative sum of daily log returns within a month as an estimate of monthly volatility. We can take this idea further to apply to intradaily log returns and derive the realized integrated volatility. We call intraday data if we observe multiple observations of the time series throughout a day, for example, the multi-minute level high-frequency data. Thus, the realized volatility of the intraday return is the sum of the squared intraday returns. However, this estimator has been demonstrated to have a serious limitation. It does not account for the effects of market microstructure. When using very fine timescale data, minute or seconds, the variance estimator will be inflated by the presence of microstructure noise. The finer the time scale, the larger the variability due to the microstructure noise. To address this limitation, many estimators have been developed in such a way they account for the microstructure noise to some extent. Such estimators have been defined based on multiple summaries of the intraday return data, such as the closing and the opening price within day t, the highest and lowest price within the day, among other summaries. The 5 estimators provided in this slide are examples of such estimators. One effective estimator in accounting for the microstructure noise has been introduced by Yang and Zhang in 2000, and it's a function of the normalized close, open, low, and high log returns. The final estimator is a weighted sum of multiple variance estimators. Statistical properties of all such estimators can be found in research papers published in the financial literature, and they rely on more advanced statistical theory. In summary, in this lesson, I briefly introduced the idea of variance estimation for high-frequency data. Thank you.